Thanks, Freddy. Thanks for the very nice seminar. Yukin, you had a question?
So in the first part about the jets, I was wondering if you can get the transition if the forcing is not is deterministic instead of random forcing.
Yes, you can. Yes. Actually, the way you force the system doesn't matter so much, because for this first case, the forcing is then mediated through the turbulent interaction, and basically the way we can describe this in a quasi-linear way, just like Steve is used to do, and then we see that it change a bit the parameters, but the basic mechanism and the basic way the zonal flow has been forced doesn't matter much. Actually, in a two-layer model, we have used deterministic forcing, and in this two-layer model with a deterministic forcing, we also observe a similar bistability and similar transition between different numbers of jets.
And how do you pick the values of the parameters, say beta and nu? Do you need to, I mean, is it very general? You can just pick some beta and nu and you can see the transition, or you need to search through the parameters, the value of the parameters?
So it depends for which application, but here for the jet, for the Jupiter jet case, I mean the parameter beta here, when you work in non-dimensional unit, it's actually a ratio of what is called the Rhine scale to the scale of a domain, and this is what controls the typical width of a jet. So when you change beta, you change basically the number of jets. So changing beta, it was known before that you can go from 2 jets to 3 jets to 4 jets. And this actually, for the real Jupiter atmosphere, what's happening is that beta actually change with the latitude. And that's why the jets are larger at lower latitude and then become thinner and thinner. And so the way beta changed the width of the jet was something that was well understood for a very long time, since the Rhines, basically. And so here what we knew how to get 2 jets, we knew how to get 3 jets, and so we just picked an intermediate value and check whether there was bistability. So a nice way to look for bistability is actually to make exactly what we did here, is to make hysteresis experiment. You smoothly increase your forcing parameter, and then you go backward, you smoothly decrease it, and then you check whether you follow the same path or not. This is a very efficient way to find bistability range if you don't know where they are.
Okay, thank you very much.
David, I think you have a question.
Yeah, well, it's sort of partially been answered. I was going to say I thought the 2 bits looked kind of different in that the first bit I could see that you might have solutions with 3 and 4 jets and you just kind of kicked it between them, whereas in the second bit you actually got this hysteresis loop, which is different. But if I understand it, you're saying there is a hysteresis loop even in the 2 versus 3 jet.
Exactly, yes. I am not showing you a picture, but we can do that. So in a sense, the second bit is less advanced. So we were looking for the hysteresis and the fact that we have a bistability range. And now we found it, we know how to control it. And so we will try to find the transition, the spontaneous transition from one to the other. But we still need to, there's still work to do that.
Okay, can I ask another one? I mean, the obvious problem to many in this group about abrupt transitions is, of course, the geodynamo and reversals of the Earth's field.
Yeah.
Can you say anything about that?
So this is geodynamo, right? Or no, this is
That's probably VKS, is it?
this is the VKS dynamo. So no, the only thing I can tell you is that we are working with some colleagues in Grenoble to try to apply these methods to do that in MHD numerical experiments.
Right. Okay.
But no, I mean, what's happening is that often people get such transition in state which are close to the bifurcation to turbulence, because it's easy to get them numerically. But then when you go in, the more you go in turbulent regime, the more difficult it is to actually get transition, because you have to, the numerical computation cost more and more, and it should last longer and longer. And so this is the whole point of our approach. I mean, to try to bypass the extremely long numerical simulation. So hopefully we will be able, somebody, not me, but somebody else will be able to do that in the future with MHD problems.
Okay, thank you.
Steve, you also have a question?
Yeah, on the second part of the talk, Freddy, you showed a kind of linear response to a forcing Q, and then you had a formula for the form of the forcing. Was that based on some kind of quasi-linear approximation?
Yes, yes, it's even yeah, exactly. It's even simpler than a quasi-linear approximation. Here it's a sketch of a quasi-linear approximation, because we this formula we have obtained them. It's just the same ID, but in order to do analytics, we have assumed that U is a constant.
Okay.
It depends on the latitude.
Yeah.
And then the model is the simplest possible one. It's the linearized shallow water equation. And
yeah,
so
but sorry.
With all this simplification, we were able to get this formula that I have shown here.
Yeah, that one. Yeah, exactly.
But so obviously it is not. It gives you the right physics, maybe, maybe not. Maybe you have forgotten something somewhere, or you don't know exactly. So, but certainly it helps you a lot to think and to try to understand what are the good control parameters.
Yeah.
And then we want to an axisymmetric model to check this using this quasi-linear formula, actually.
Yeah, thank you. Makes sense. Great.
And then we want to check it in real models.